welcome to week 2. We're going to pick up where we left off last week. Few announcements. Textbooks have not shown up yet. They're official ones. So at least I gave you guys enough to get through the first 3 or 4 hybrids. And if it comes to it, I'll keep slicing and dicing until you can do all the hybrids. I'd rather not do that, but we're going to go with it. Today there's a lot of talking on my part. Not my preferred way of teaching, but I got to get through the theory, some of the theory right off the bat. So today's a theory heavy day. I'll be putting up the PowerPoint presentation probably at the start of the next lab. I will do my best to get the recording up as fast as I did last week. I've tweaked my settings, so hopefully there's less clicking in the audio. For those of you that have actually rewatched part of that lecture, you notice I can pick up every keystroke for the people in the first 4 rows for some unknown reason. Apparently this recording software I switched to is very, very auditory sensitive. But I'm running it through something else that'll clean it up, so I'm hoping the combination of 2 sets of settings will get rid of a lot of that. So without further ado, I'm going to get started. And away we go. So today we're going to cover the basics of database design. Essentially, I'm going to cover types of relations and tables. I'm going to talk about ER diagrams. I'm going to talk about the basic parts of tables and my naming conventions. Every prof has slightly different naming conventions. Some people follow really old school ones. I follow very modern ones. I guess that's the difference between following the textbook and dealing with code in the wild. All right, so I'm going to start off right off the bat with something called the types of tables you'll see. Last week I vaguely discussed things, and I'll get into more details with some of the stuff in a minute. But in database design, there's 2 terms that are interchangeable, sort of. One is tables, the other one is entities. Essentially, a table is a physical representation of an entity. An entity is a place, a thing, a person, an activity. Those are entities. Tables are the physical representation of the entities. So some diagramming software use the term entity, such as Toad. Others use tables. When you're talking about a database, normally it's referred to as tables. Now there's 2 common types of tables when you're doing database design. And I get this right off the bat, right in the slide, because people sometimes have a hard time grasping this concept. The first type is called the reference table. People call them lookup tables, reference tables. They have a few other names, but essentially the point is it holds a list of data. You know when you go to a website and you hit a drop-down and there's a list of options in a drop-down on a form? That's coming from a reference table. It's a table that holds a finite list, but that allows other people to edit the values so the list can change dynamically without requiring recoding of the application. It usually has only 2 or 4 fields. Towards the end of the presentation, I'm covering what most of those fields would be. And then you have what's called a regular table. And regular tables contain standard regular data. A person, their name, their address, phone number. That's a regular table. It contains details. It has several fields normally, much more than a reference table. And it can be a parent or a child. I'll be covering what that means in a few minutes also, but I had to get the overview out of the way. So a table is an entity. Depending on what kind of entity it is, it has different meaning and different use. And I got to mute my phone. Bad teacher. All right, the other part that you need to know about is attributes, also known as fields. An entity has attributes. You all have attributes, right? You have names, you have dates of birth, you have what sex you are, what height you are, how heavy you are, or how light you are, depending on how the case may be. I'd fall more in the first category than the second. But those are attributes. They describe an entity. And essentially an attribute is a property or characteristic of an entity or of a relationship type. That relationships are explained a bit later. But essentially there's certain classifications when you think about attributes. Is it required versus optional? So when you're creating attributes of something, you have to decide whether or not it's required or not. In our society, you are required to have a name. That is how it is. You don't get to go through life with as simple as your name unless you have too much money. there's the reference. Otherwise there's certain things that are optional that you may have. Do you have an address? That might be optional. You might be living in a cardboard box with no address. Versus you might have a physical address. It's optional. Or you may have a phone number, you may not have a phone number. Or you might have a landline, you might not. You might only have a cell phone. Those are optional attributes. Is it a simple attribute or a composite attribute? For example, your date of birth is a simple attribute. It has one value. A composite attribute is like an address. What makes up an address?
Number and street.
Number and street. What? City, postal code, province or state, country. You might even have a secondary address like box 12 or suite 100. That's considered a composite attribute, as in it's an attribute made up of many values. And then there's single valued versus multi-valued attributes. In other words, this attribute can only have one value, or this attribute can get its value from a list. A good example of multi-valued attribute is a reference table. It gets its value from a list somewhere else. It can have more than one value applied to it. There's one last one, which is stored versus derived attributes. A stored attribute is your date of birth. A derived attribute is how old are you today? We don't need to store how old you are because we can figure that out. Therefore, that's called a derived attribute. We can derive the value without storing the data in the database. It's a good thing to be able to derive the values because you're putting in less in the database. It requires more overhead processing, obviously, because you've got to calculate stuff, but you don't need to store it. For example, another example is when you're buying groceries. Your bill at the end is a derived attribute. How much each item costs you? 5 at $1.99. You don't need to store how much that line total is because you go 5 times 199 equals blank. Then you add up all of those, you have a total. Those are derived attributes. Those are attributes you can calculate without having to store. As a rule of thumb, you try to store as few derived attributes as possible because it's possible that you can corrupt it later on if the data changes. You realize, for example, how many of you order off Amazon? Probably most of us, right? Any of you ever put something in your shopping cart but not check out right away? And then 2 days later you get a notice saying, hey, by the way, the price changed. You know what you had in your shopping cart? A few have had that experience? Yeah. Therefore, your order total changed because the value was in the cart changed before you finalized the transaction. Therefore, it's a derived attribute. If they'd stored a static one, they would have actually have to run database updates to fix everybody's orders that aren't checked out yet. So, it's an example of a derived attribute. And then there's identifiers. There's actually a whole slide dedicated just to identifiers later down the road. But these are what's used to identify a unique piece of information. As far as you guys are concerned, you each have a number as far as the school is concerned, your student number. That's your identifier. As far as the Canadian government is concerned, and if you're a Canadian citizen of some sort, or a landed immigrant, you have a social insurance number that identifies you uniquely to the government. Those are your unique identifiers. Okay, now we're going to start talking about diagramming. In the lab, last week's lab, I had you guys make a diagram following my instructions. And some of this stuff, some of these words should actually look familiar now because I had you doing it. An entity instance. So this is actually terminology straight from the textbook because it may show up on an exam somewhere along the way, so that's why reading the textbook's important. Entity instance. An entity instance is a person, a place, an object, an event, or a concept, just as I described earlier, right? An entity describes something. The table is the actual physical paper version of the description, essentially. We could describe something verbally, but then once you put it down on paper, then it becomes an actual table, as opposed to just being an entity. And then there's entity types. Normally, those refer to tables. There are a few other kinds of entities, but for this course, essentially, you're talking about tables. Relationships. Those are the connections between entities. For example, in this room, there's a bunch of different kind of relationships. You're students, I'm a teacher. The relationship is one to many to one. Right? I have many database students, but you guys have one database prof. So many to one, or one to many. Essentially, it's based on connections. That's a relationship. And in a couple of slides, I'll cover what the different kinds of relationships there are. And there's a relationship type. Like I said, I'll be covering that in a bit more detail. Attributes, I described those also earlier. Those are properties, characteristics of an entity. Essentially, it's just an attribute that describes something. Your name, your address, etc. All right, so a bit more detail about entities. I covered it a bit already, but we're going to go through a bit more. Okay. There is an entity type, an entity instance, and then the entity. The entity is a person or a place. I described this fairly well already. Or it could be a concept in the user's environment, which we need to maintain data. For example, a concept that some profs maintain is attendance. Right? Attendance is a concept. Grades are a concept. I maintain grades based on real-world data. Those are concepts that are logged. Whereas I keep grades about a person, which is a student. Therefore, then you can see the relationship, right? Teacher, student, grades. So I have many students. Each student has many grades. So it starts building up, sort of like a branching kind of environment. Entity types. So it's a collection of entities that have common properties or characteristics. In other words, tables. They all have fields or attributes. That's an entity type. There's a few other types, such as views and triggers and stuff like that. Those are different kinds of entities. And then you got an entity instance. And it's a single occurrence of an entity type. So an entity instance would be student. Whereas I could have an entity type called person. Okay, in here, we're all people, hopefully. Hey, there might be androids. Get your tinfoil hats out. But there's different kinds of entity instances, but when you create a database, you only create one instance. For example, there's 120 odd students theoretically in here. When I create a database, I'm not going to create a table for every student. I create a table that contains the students. That's an instance. The table is a single instance that describes one or more students. You don't create fields for every student. You just create one set of attributes, then you fill them out one after another. How many of you have used a spreadsheet? Okay. Oh, wow, that's like the best number I've had yet for that one. We're probably teaching you guys how to use Excel in high school now. But essentially, you can picture it this way, right? Columns and rows. Each column is an attribute. Each row is a collection of attributes. That sheet is an instance. So sheet A is an instance. Each of the columns is a different attribute. So you could have, name, phone number, blah, blah, blah. When you go across for each row, that's just collections of data. But basically, each Excel spreadsheet is the equivalent of an instance. Okay, I'm going to read a note that's on this slide because there's notes on some of these slides that I ripped off from somewhere else. It is important to distinguish an entity instance from an entity type. For example, an entity may be John Doe, which is a particular person. The entity type is a person. So I just used that word as a concept. When you're creating the ER diagrams, there's boxes that describe the different entities, which you guys experienced last week's lab. I had you guys create an entity and populate it with attributes. Essentially, when you create a table on a diagram, those are entity types. Entity type person, entity type student, entity type class. Entity type class room. Entity type laptop. Sort of laptop when it's a Mac. I just make fun of Macs. Don't take it personally. I just make fun of Macs because I got to pick on something. I used to make fun of the Alienwares, but there's no Alienwares anymore in the classes almost. So it's not fair for me to pick on the Asus machines because they'd be outnumbered a lot. If I look at all the glowing logos, that's a lot of Asuses and MSIs in here. Holy cow. All right, so back. An entity. Here's how you describe an entity. An entity should be an object that has many instances. So in other words, a student. There's many students, many instances. An object that will be composed of multiple attributes. You're not one-dimensional beings. There's many parts of you that need to be described. An object that we're trying to model. In other words, it's something we're trying to model in the databases, and we're trying to collect information, collect data. That is what an entity should be. What it should not be, shouldn't be a person using the database. By that, I don't mean a user logged into the server. I'm talking the actual person physically using the database. That is not an entity. Or the output of the database, such as a report, the actual finalized output. The definition of the report might be an entity, but the actual output is not. You should never store the output unless you're trying to cache for performance, and you don't actually store the output in the database, you store it somewhere else. That's what an entity should not be. Okay, now to talk about required and optional attributes. If you look at this, this is actually in the textbook, which you don't have, you know, just call it the way it is. This is a sample sort of what a, what's the word I'm looking for, the contents of a table with the attributes they would have. So you got a student, I got a laser pointer now. You got an entity type, student, you got different attributes. So these are the different things that make up a person going down this side. So student ID, their name, their address, home, city, state, blah, blah, blah. You got the data types. I'll be talking about data types next week, about all the different kinds of data types. But essentially these describe the types. So the student ID is a character field, and it's 10 characters long. You guys, hope by now, I know it's early in the term, but by now, if I know you know what a character is, it's a letter or a number. And because it says it's 10 long, that means that it'll hold 10 characters. Now they got the required or optional. So when it's required, it means that you must have it for every single instance, or every single row of data you put in, that must be populated. In other words, if I create a database of these students of my own, and I decide that your name is required, I cannot add your information to my database if I don't have your name. The server will say no. You're not allowed to do this. And literally, that's pretty much what it says, no. Check your data, you're missing stuff. And then they give us some sample stuff here. Now in this one here, they did it cute. They made absolutely everything required except for the student's major, because he kept it simple. But essentially that's an example. So an optional, such as last one down here, means you may have a value or you may not have a value. It's up to you. Sometimes you don't have all the information. You'll see this often. You'll see when you're filling out a form to register, we'll ask you, what is your phone number? Required. Your cell phone number, that is optional, because you might not have a cell phone number. Nowadays, they actually got to go the other way around and say, is your landline required? Because you might not even have a landline. You'll see a lot more websites now, a lot more websites. Nice English. You'll see now they don't say home phone number, work phone number, cell phone, they just give you phone number. And then you put the one that applies the best because the data started evolving. But there once was a time where they'd have a cell phone line, and they made it optional because not everybody had a cell phone. It's just how it is. Okay, simple versus composite attributes. Now, a composite attribute is something that has meaningful component parts. In other words, an attribute such as an address, that is a component attribute. Why? Because it's made up of multiple meaningful pieces. And as a rule of thumb, when an attribute has multiple component pieces, you don't normally want to model every component pieces, not just have a box that says address. I'm trying to come up with an example that works better for level 1 students, because normally by now you've done certain kinds of work that I can rely on. Now let's see, we'll just go with it. If you have an address field, it's just one big block of text. So you got your whole thing, 123 some street, comma, Ottawa, Ontario, comma, Ontario, comma, K1Z, 1Z1. And you need to find an address, a specific city. And you need to search through a big blob of text. Which one do you think is better? To be able to search for a specific piece of it, or just have to search through the whole thing? Searching for a piece is easier, right? If you have a field called, or an attribute called city, you have all the cities listed inside just that one field, and you want to say, give me everybody in Stittsville. Theoretically, then you just can go search in the city field for Stittsville. Or you want to search for Cobden. You go looking for Cobden. And then all it does, it returns out to you everything that's Cobden. When you got the big field, and you search for a substring search, which you guys will learn later, you look for the word Cobden. Well, not far from here, there's a Cobden Road. There's a Cobden Road, great pizza shop on Cobden Road, but there's a Cobden Road. Whereas there's also Cobden, Ontario, which is up the highway about an hour. And you'd end up with both matches because you're searching for just Cobden. So then you end up having to do weird positional matching and stuff, and it's not easy. So you tend to want to take a composite attribute and break it down into simple attributes. Composite attributes are a bad thing, because it means that you're going to make life hard for everyone. All right. Then you got multi-valued and derived attributes. A multi-valued attribute is an attribute that can have one or more values. Normally you use a drop-down, but they can have more than one skill. I discussed what you do with those later. And then you got derived. I already covered that in detail, so I don't think I need to go back through that again. Okay, this is the important one for everybody. This is like the most important concept probably in today's class. Identifiers, known as keys. An identifier is used to find a single instance of an entity. So in other words, a single row of data. If I want to find a specific student in this class, and I don't know their name, but I know their student number, I can just call out their student number. Then everybody madly looks at their student ID, because probably most of you don't have your number memorized yet. And then you're able to respond that, yeah, you're such and such a person. That's your unique identifier. And there's two kinds of identifiers. Like everything in database, there's two of everything. There's simple versus composite. Simple means there's a single identifier, single key that identifies you uniquely for the system. At the school, we use student number. So your student number is your unique identifier to the school. The composite is when you have a combination of attributes that make you unique. As a rule of thumb, composite attributes are a bad thing. Having composite keys are a bad thing, because it means that you end up having to rely on multiple pieces of information to make sure something is unique. So as a rule of thumb, from what I just said, what you want to have is simple identifiers, simple keys. And just so you know, when we start talking later about this stuff, these are primary keys. The primary key, from here on out, I'll be calling this primary keys, because that's what they're called in a database. The primary key is the identifier used to uniquely identify a record in the database. Each table should have a primary key, and if you do your database design correctly, your primary key is made up of one field, and only one field. If you have more than one field, you're not achieving a certain level of normalization, which is next week's topic. But you're not going to achieve a certain level of data uniqueness, because you're relying on more than one piece of information. Now, they have something else called candidate identifiers. when you first start doing database design and you haven't identified your primary key yet, you're looking at the data and saying, what in this could be a unique identifier? A person's name. That could be unique, theoretically. But, actually I know there's several repeated first names in this class. I don't remember them off the top of my head because I don't remember names. Suck at names. But I know there's a couple of repeated first names. So I can't use a first name as a unique identifier. And there's repeated last names. And I can't use that as an identifier. But a candidate identifier would be first name plus last name. But that gives me a composite key, where I'm relying on both pieces being there all the time, and that the combination of the two can never repeat. And believe it or not, I've actually had two Lisa McIsaacs in the same class 3 years ago. Literally had two ladies in the class with the same name. And they were both blonde. Naturally blonde. So it was a nightmare. For someone who can't remember names, it was awful. But it happens. So therefore, could first name plus last name be reliably used as a key? Theoretically, yes. In practice, no. Therefore, it's not a valid candidate identifier. But everybody here has a SIN number, theoretically. Unless you're an exchange student, then you have something else. Therefore, SIN number could be a candidate identifier if I was only dealing with Canadians, actual Canadian citizens, landed immigrants, and a few other categories where you get a SIN number. But if you're an exchange student, all you have is a student visa number, then you don't have a SIN number. At least last I heard, unless that's changed. So then, again, SIN number is a very good candidate key depending on the data. So as a group, what schools do to avoid these kinds of problems, they give each of you a unique student number. And that becomes your identifier. It's a very good candidate key. Why? Because it actually goes, 99154, 99155, 99156. It just increments once you've registered. And it's always unique for each of you. Therefore, your identifier / primary key is your student number as far as the school is concerned. It's a simple identifier because it's only one field, and it's a strong candidate because we know it's unique. That's an identifier key, also known as a primary key. Every table should have a primary key. Later on, when I get into the part of the course where I discuss the naming conventions and what should be in a table, I'll actually tell you what these should be called. Oh, skip that one because I just finished talking about it. No, I should read my next slide before I keep talking. Defining attributes. Okay, now we're done talking about primary keys. Now we're going to talk about the rest of it. And the attributes that make up an entity. So, when you're defining an attribute, you should state what the attribute is and probably why it's important. Is your name important? Probably. Is your date important? Usually. Is your gender important? Depending on how you look at it. Your address important? Yes. But there's some of it might not be as important. Do you have an address too, such as a P.O. box or a suite number or something of that nature? No, that one's not as important. You need it, but it's not as important. You should make it clear when you're defining a new attribute what is to be included in it. Example, if the attribute is about your name, should you be allowing people to put in dates of birth? Obviously not, because it's the person's name. Unless your parents got really clever and they gave you a combined first name and they called you April 1st. Hey, my son dated in April. All she needed was a compound first one, right? April 5. Damn, we know what her date of birth is. But that, it's just people using stupid names. But realistically, usually an attribute, you make it clear what's supposed to be in it so that you know what that data is meaningfully. So in other words, if the attribute is a name, You give it a name, call it probably name, and it holds names. If you have to have an alias, and by an alias means if you have to have some weird reason why the attribute's got a weird name, document why it has a weird name. As a rule of thumb, there's no excuse to have weird names. But in practice, there's always an excuse for a weird name. When you're documenting the database design, you should state the source of the values. So this is when you do documentation. Every programmer's worst nightmare, having to write and explain why certain things are the way they are. We hate documentation. It feels like a waste of time. But when you're the guy inheriting the project from someone else, you love it when they give you documentation. You should explain where the data comes from. Is it something they can change once it's been sent? Your name. Can your name change? Of course it can. Can your date of birth change? Probably not. Can your gender change? Apparently lots of times. Hey, I didn't pick on anybody in particular that one. It's completely fluid now. I got a 16-year-old at home that keeps, every time I start on this, she gets mad at me, right? She goes, Dad, you're not supposed to talk like that. Okay. And now it's just everything's fluid. You should specify whether it's required or optional. Your name is required, your date of birth is required, your cell phone number is optional. Now, if there's numbers involved, maybe you want to state what the minimum and maximum values are, right? I'm doing a database of people that are currently available in this class. Therefore, theoretically, I could say you're not allowed to have a date of birth before 1910. That 100-year-old student is theoretically possible. 110-year-old student, not so likely. But you could put in a range. And also, I probably don't want to allow dates of birth after 2012? 5-year-olds? 4-year-olds in class? No. That's maximum number range. That's usually in documentation, not implemented in the database unless there's specific hard-coded reasons why. For example, in an order, you may not want to allow negative quantities. Why? Because should you allow someone to buy -1 laptop? Probably not. Maybe if it's a return, but that goes in differently. It should go in differently anyways.
Or he's selling it to you?
Hey?
Or he's selling it to you?
Sign it to you?
Selling it.
Yeah.
-1.
In -1 inventory.
So then you're...
But in the order is a +1.
Yeah.
But realistically what it is, it's inventory minus sold gives you the real number. It's a derived attribute on hand. Take in stock minus items sold, it gives you the on hand value. Theoretically derived. It's not that simple. I cover an example like that way late in the term. And then you should indicate what the relationships are with other attributes in documentation. So this attribute gets its values from this entity kind of thing. Or this attribute's required if this other attribute is here. That kind of stuff. Okay. There's different kinds of relations. And Brentfeather basically I'll cover a little bit later on with the different verb terminology, because there's, depending on where you went to school, they use different terminology. So if you go to a university, they use a certain terminology. You go to a college, you use a certain terminology. You go to, like in California, the profs may use different terminology because most of them invent it as they go, because they think their words are better than the other guy's words. So I'll be going through the different kinds of wording for the same thing. So it sounds like I'll repeat myself a bit. So there's referential integrity relations. That means that these are the ones that make sure that the rules are followed in the database. So you got the one-to-many. Earlier I made an example of that, right? One prof, many students. One mother, many kids. One kid, one mother. That's how it usually works. So one to many, normally what happens is a parent table has many children, teacher has many students. There's a primary key, usually in the parent. And then there's a foreign key, which is usually found in the child tables. Remember last in the lab when I made you click on the two tables and draw a line between them? It would grab the name of the primary key in the first table and actually copy it to the second table. Then you renamed it. If you haven't done that lab, congratulations. I'm describing things you should have done by now. But essentially, that's the parent-child relationship, and those are the parent key and the foreign key. You got one-to-one relationship, where every table in a relationship must have a matching record. That means that one table has a record, the other table, they can only have one between the two. Not used very often. It's usually used for security purposes. You got many-to-many. So that means that there's cross-references between many tables. And that means that, for example, if you want a good cross-reference, right now I've got one teacher, one prof for this class. But if you take this program, you got many students and many instructors. That's a many-to-many relationship. So student has one prof for this course, but in the program, you've got many students with many profs. Those are many-to-many relationships. So those are referential integrity. There's logical relationships also, or relations. This refers to how tables are connected. You have something called a singlet. In actual fact, of all the database profs, I'm the only one I've ever heard use that phrase, a singlet. Why am I the only one? I have no idea, because I've been working in the database industry for 20 years, and I've seen it used out in the industry lots, but never actually in a classroom. A singlet. It's a single standalone table. This table has no connections to anything else, none whatsoever. A good example is a log table. Information gets logged into that table. It's not actually connected to anything else directly. It stands by itself. You got a parent-child. In other words, you got a parent table and a child table. There's usually a primary key and a foreign key. Usually the way it works is it's a reference table going to a regular table. A good example of this would be a customer is a regular table. The reference table might be a list of provinces or countries. The countries is the parent, the customer is the child. Because each child can only ever have one value from the parent table, but the parent table can have many records associated to it. Parent to child. Yeah?
No citizenship in that create two?
Depending on what countries that allow dual citizenship, theoretically, yes, then it's handled a different way.
Yeah.
But realistically, when you're talking about addresses,
Yeah, and most times it's more one.
you have, as far as the school is concerned, you have one address.
Yeah.
Now, you might have a mailing address, but you have one primary address. Then there's the many-to-many. So end-to-end. Tables cross-reference each other. This is being used less and less because it's actually nightmarish to use a many-to-many relationship. It uses, now there's a phrase that's coming in popular use. Unfortunately, it's not in this textbook, but a lot of coding environments are coming up with this terminology, and it's called has and belongs to many. Habitum. Has and belongs to many. What happens is you've got one table and another table. What you end up doing is you create a table in the middle that connects them. So it's a cross-reference table. It used to be that you had tables that did this. Table 1, table 2. The many-to-many would go, this table goes this way, it goes that way, it goes this way, then it goes this way, then it could go that way, then it could go this way. That was a has and belongs to many. So suddenly, you wanted to remove a record from here, you would have to chain through all the tables one after another. And eventually, you clean it all out, and then you got you're missing tons of data. And I've seen a case where somebody wrote it, and there was one parent record in this table, they nuked it, and nuked everything. Cleaned up both tables. Tens of thousands of rows of data are gone. It wasn't a happy day. So people have come up with something a little more clever. They've created, as a has and belongs to many table, there's a different name for it, and I'm drawing a blank at the moment. And the way it works is like this. So these two tables are never connected directly. They're connected using a third table. So what happens is this person becomes a broker. This table becomes a broker. And it uniquely identifies every relationship between the two tables. And if you need to break a relationship, you only need to delete one row of data from here and then the connection's gone. So it's a bit like, for example, I'm standing here, I'm your prof, he's the broker in the middle. We eliminate him, we're no longer connected. Right? Same thing, if I go in this direction, right? There's you, and then there's the guy in the blue shirt. I eliminate you, I'm no longer connected to the guy in the blue shirt, because I'm using you as the in-between person. That's what these tables do, is the in-between person. And then there's one more logical unit, and it's a master detail. And what the master detail does is, when you have a table that has a lot of information, and it has another table that has a lot of information connected to it. Best example is, I'll use Amazon orders. You have many orders, and on each of those orders, you got all kinds of information, right? You've got when was it placed? Where is it being shipped to? How was it paid for? But each of those orders can have many things inside of it, right? You bought a pair of shoes, a tripod, and associated other items that you place in that one order. So it's a master detail. The master is the order. The order has all kinds of information in it, but the master is the order. The details are the order lines, the things you bought. It's master detail. All right. Remember earlier I was talking about the different kinds of relationships and how I'd be using a different set of terminology? This is it. Degrees of relationships. And I've actually got a little picture in a second. Degrees of relationship is the number of entities that are participating in it. You've got unary, binary, and ternary. Man, I hate that terminology. I'll bring up the picture. Okay. Unary. It's an entity that's related to itself. For example, do you ever use a website that has basically like a series of categories, and every time you click on a category, it jumps to the next one down? Then it shows the next list of categories, and you click on that one, it drops to the next one down? That's a unary relationship. They didn't create a different table for each of those ones. What they have is, they've got a series of tables, and it just refers to itself, or itself and self-referring. That is a unary relationship. It's an entity that refers to itself. At a company, for example, when you go work, they have one category called employee. However, employee A probably has a boss, right? That boss probably has a boss. And then, onwards and onwards, depending on how big the company is. But each of those layers, they're still all just employees. Just one employee refers to another employee. So basically, it's one piece of information referring to another over and over and over again. You got binary. So two different kinds of entities related to each other. One good example of that is course, student. A course has many students. Thus, there's a relationship between two different kinds of entities. That's known as a binary relationship. There's ternary, and actually keeps going past ternary, but essentially, after ternary, we just stop giving it names. It means that there's three entities participating in this. For example, this course actually has three entities when you think about it, right? There's the course, there's the students, and then there's the person teaching this course. Therefore, it's a three-way relationship. There's three pieces making up an actual valid value. That's what they call a ternary relationship. Well, that pretty much explains that. There's not a lot I can say past that, other than those are the three levels, right? Unary means it's self-related. Binary means it's related to one other thing. Ternary or further past that means it's related to multiple things. All right, cardinality. Earlier, remember I was talking about, there's one to many, many to many, one to one. There's also the cardinality. It's the other phrase they use. There's three sets of phrases people use, and the one I just did before, which was the degrees. You got the cardinality, which is one to one. It means it's one entity in a relationship has to be related directly to another entity and only one other entity. That means, for example, if we did talk about parents and children, imagine a mother can have one child and only ever one child. No more than one. Period. Genetically impossible to have more than one kid. End of story. That would then become a one-to-one relationship because it's a one-way, there's no more. One-to-many is how things are right now biologically. You got one mother has many kids, but each kid can only ever have one mother. Then you got many-to-many, where everything's cross-connected. For example, it's students and courses via programs. This program has many courses, and there's many students in this program. That's a many-to-many. That's cardinality. In a minute, I'll have a diagram up on the board, on the screen. Cardinality constraints. That's the number of instances an entity must have when it's related to something else. For example, for this database course, the lecture section, the rule is as follows. I can have many students, but you guys can only ever have the one teacher for this course. Unless you replace it and get another teacher. But you can only ever have one teacher at a time doing the lecture. And then there's what they call minimum and maximum. If 0, that means it's optional. And I'll put up the slide in a second. And if it's 1 or more, that means it's mandatory. So I'll just bring up the slide. Okay. So if you guys did the lab, you'll notice some of the notation that was on that screen, right, where you had something called the crow's foot. These things, right here. This end over there. Those are cardinalities. You see something that looks like what they call the crow's foot because, well, obviously it looks like a little bird foot drawn sideways. That means that it's a many relationship. That means that there's multiple values. This means that there's one. This little circle means it's optional. If it's a solid line, it means it's mandatory. That's the notation on the diagram. So on this diagram, they've got this, right? You've got a patient and a patient history. It means that a patient history must have a patient. In other words, you can't put patient history without a patient in. It's just, I can have a history of a patient without some sort of patient associated to it. And this means that the patient is required, and that if a patient is created, it must have at least one entry of history. This is actually a little uncommon, this setup, because when you create the record in the database, how can you have a history? It's a chicken before the egg moment, right? You got a patient, the patient must have a history. But how can you put in a history if you don't have a patient? So normally, by the way, this is right out of the textbook, that's why the slide's this way. They use this as the example to show you. But realistically, a patient can have 0 or more history. So instead of having the solid line, the crow's foot, you'd have this guy here upstairs, up here. So you'd have the circle and the foot. So the circle here and the bird's foot there. That means a patient can have 0 or more history. In other words, the patient was first created, and as soon as this is created, then you'd have a history, because then, there's history that the patient was created. And they show examples here. Mark had a visit, Sarah had 2 visits, Elsie had 1 visit. Essentially, that's, the many, one to many. Okay. Associative entities. About 5 minutes ago, I used the phrase has and belongs to many. That might ring a bell if you're paying attention. If not, you'll be watching the recording. But the old terminology for this was called an associative entity. And this is part where teaching level 1 makes it a little harder, because you guys haven't learned about something called arrays yet, which is a somewhat more complicated topic than what you guys are learning in programming yet. But essentially what an associative entity is this, right here. All right? It's an entity that's used to connect entity A to entity B via entity C. That's the question on the slide. When should a relationship with attributes instead be an associative entity? So when should you use the connection directly between two tables as opposed to using a third-party table? Essentially, we should use a relationship with attributes when all the relationships are many-to-many. In other words, there's always many-to-many between the two sides. If this table has meaning without either of these two tables, then you should be using the relation with attributes as opposed to an associative entity. In other words, if this table can live without these two, then it's not the right kind of table. It shouldn't be used as an associative table. It should be used as a regular table. Because essentially, this table cannot live with, it should not be able to live without its donor DNA. Without the two parents that connect it, it shouldn't exist. The other thing is if this table can participate with, you have another table up here, and we're just going to draw hash marks on it. This one, you can create an instance of this every once in a while with only referring to this guy, but not to these guys. You shouldn't be creating those either. That means at that point in time, you're looking at creating a completely new relationship, not an associative entity. Because associative is only, it must have some of all of the things that participate in it at all times. That's an associative entity. Otherwise, you're looking at a relationship with attributes. In other words, you have a table with many different fields in here, and some of them are optional, and some of them aren't. And essentially, certain kinds of ternary relationships should be converted into associative entities. That means that if you've got certain kinds of ternary relationships where you've got student, trying to come up with a really good example. Okay. Okay, this says student, that says skills. Okay, so you have a basic associative entity. We could well call this one SS because I have a lot of room. A student can have many skills, and skills can have many students. So that's an associative entity. That means that, in this case, all you can have is a student and a skill. On the other hand, we have another table called a course. Call that student course. And in here you have grade, start and good. Okay. A student can have many courses and a course can have many students. That's fine. But suddenly we have other things in here. We have a grade, we have a start date and an end date. So this is what they call a relationship with attributes. This is an associative entity. An associative entity normally has three fields. And it has the primary key, and it has two foreign keys. And a relationship with attributes has these three fields, plus more. Excuse me. That was a little gross. I'm coming down with a cold, so I'm running ahead of my throat. It's starting to go on me. That's the difference between what they call an associative entity and an entity with attributes. An associative entity with attributes. Realistically, how often are you going to use this terminology? Not very often. Is it going to show up on an exam? I haven't seen the final exam yet. So theoretically, yes. You should know what the difference is between essentially an associative entity and a relationship with attributes. They say that's all it is. One with attributes is used to describe something a little for the relationship between things a little further. And a good example is this course, right? I am connected to you via whatever the magic table is at the college for this course. And the connection between you and I describe many things. When do I start teaching you? When I stop teaching you, what grade did you get in this course? Whereas, if it was just an associative entity, it'd just say you're connected to me, and you're connected to Howard. Howard is connected to you and connected to someone else. I'm connected to you and connected to someone else. That would be just a straight up associative with no other describers. It just talks about the connection. The other one describes the connection. Right on schedule. Since my watch stopped keeping track of time. Okay. There's one last thing, realistically, before I get into some of the other stuff. I've only got another 5 slides left. The check constraint. A check constraint is an integrity constraint. This sounds a little funny because it's a little bit out of left field compared to what I was talking about. Well, earlier, for example, one of the check constraints that exists intrinsically in all database servers is required or not required. This is known as null or not null. If it's not null, it has to have a value. If it's null, it's optional. That is an integrity constraint. Some database servers allow for more robust constraints, which means when you enter an instance of an entity, also known as a row in a table, where I'm giving you both sets of wording, an instance into an entity, in other words, a student in this class, or a row in the database, in the table, student in this class, same thing, 2 different terminology, I can apply certain rules to it. We can have multiple conditions. And normally the format, and I keep it pretty simple in this example, is the column / attribute / field, right? There's 3 words that mean the same thing. There's a condition, and then a value. Howard teaches you guys Java, right? Did you talk about conditional checks yet? No. Less than, greater than, equal to? No? Fantastic. I'll teach it to you first then. Then you tell Howard, Dad already taught us that. Okay. I like making fun of Howard. I've worked with him for years. Okay. Conditional checks. That's why I gave myself extra time at the end of this lecture, because I figured this was going to happen. Conditional checks essentially mean a few things. One of them is, what are you checking? What's the rule and what's the value? That's what you see right down there, right? You've got the column, condition, and the value. So the column in the database is an attribute. For example, date of birth. Right? Earlier I was joking about not allowing someone more than 100 years old in the course. Date of birth gives me a minimum timestamp. A better example is a price, not allowing a negative price. So this rule is as follows. And I have it up here, but essentially I've got a field, price, and I've got values, okay, over here. 0, actually I'm going to go -1, 1, 2, 3, 4. Okay, those are possible values. Let's just say we can have a maximum of 4 things. Then you've got conditions. that go down here. And depending on what math you took in high school, you might have learned about some of these symbols. And the symbols are as follows. And I guess I'll have to put up a little document that shows you what the symbols are, because normally this is covered. And the symbols are as follows. Greater than. Less than. Anyone want to take a guess what that one is?
Equal to.
Equal. Bang equal sign means not equal to. All right, so those are the four basic ones. There's two more basic ones and then one a little more complicated. Okay? If I go like this, that's greater than or equal to, right? So you got greater than or equal. And then we got the other way around, less than or equal to, right? Less than or equal to. I'm actually I got a little copy paste from another document, I'll just put it up on Blackboard for you guys. Okay, these are all the basic ones that you'll find to check values. In other words, if I'm saying price is not, it has to be more than 0, it would be written something along the lines of this. Price greater than 0. That's a condition check, saying price cannot be that. Or I could go quantity greater than or equal to 0. That means I'm not allowed to have negative quantities. I'm not allowed to sell you a -1 laptop. I cannot give you a -5 grade. It does bottom out at 0. It's just how it works. There are two other checks that are included. And this one has to deal with the concept of nulls. Did they talk to you guys about nulls yet?
Yeah.
Yes?
For sure.
Pretty sure?
We just covered like last place.
Yeah, nulls is the absence of value. Essentially what that means, it means that an attribute has been defined, you can create a record with it, but you don't have to supply a value. That means there's an absence of value. And with database servers, nulls become very important. Because a null is an absence of value. An empty string is a value. Because it's an empty string. You're feeding it nothing. But it's not really nothing. It's just you're feeding it an empty string. But it is a value because it's a string that's empty. Whereas null means that you didn't even give it that. And then you've got the opposite. Is it not null? So you got one last set of checks. And I'll put it on this board. The camera should pick that up, I hope. There's is or is not. And that's usually used with nulls. Is null. Is not null. That's the last set. And this one, those two are unique to database servers. If you try to use is null instead of a Java program, the Java interpreter will look at you and think you're on crack. It's going to complain and give you it's going to give you all kinds of error messages, whatever happened to be. I mean, it's the same thing if I try using PHP, it's going to go no. This is database specific. It means that you can check to see if a field has ever been given a value. In other words, I can say, is email address, I can go email address is null. Is email address is not null. That tells me that the email address is not null. That means there's something there. Whether it's an empty thing or not, it means at least I took the time to supply a value to it. Whether I supplied an empty string, it's still a value, it's just an empty string. As opposed to not giving it a value at all, then it's a null. So these are conditional, what they call conditional operators. those are the basic ones here. This one here, the not equal to, database servers have only had not equal to for about, I think about 5-6 years. We used to have to use a different syntax, and if you're crawling the internet through the internet for looking for help later on, you may see the alternate version of this, UFO. Greater than, less than. In other words, can something be greater than and less than something at the same time? No. Therefore, it's not equal to it. This is what we used to use. This is what it is now. All right? Just saying. So when you're doing a check constraint, and on lab 3, I do mention at one point, please create a check constraint of something. I don't remember what it is off the top of my head, but I asked you to do it. Just remember this format, right? It's the column, the check operator, and then whatever value you're trying to compare it against. So if I say it's not allowed to be 0, or it has to be greater than 0, it would be basically, price greater than 0. Okay. Now I'm going to take a step sideways a little bit, and I'm going to describe the basic parts of a table. I really need something to drink. Hold on. Okay. So when you're creating a database table, and by this I mean you're doing it in a diagram or you're doing it physically in the database, you can do both. All tables should have a primary key. A primary key is used to uniquely identify a single row of data. I described it earlier, but as a rule of thumb, all tables usually have a primary key. There's a description field of some sort. Some organizations prefer the word description, some prefer the word name. It's basically, that attribute describes the instance. For example, my student instance has name because it's your name. Theoretically, the school has a database essentially of all the classrooms, right? What's the name of this classroom? T119. And that would be its name attribute. So far, there's a primary key and has a descriptor field of some sort. Normally, there's timestamp fields. Now, this is something that's coming out a little more commonly now. There once was a time where you didn't care about this stuff. This wasn't actually taught, this concept. But then people go out into the field, and I've had reports back from students saying, well, why didn't you ever tell us about the basic parts of a table we'll find everywhere? Nowadays, there's 2 timestamp fields. I know you don't know what a timestamp is, but actually, how many of you have worked where they actually have what used to be punch cards? Or you walk into the grocery store and you clock in on the little keypad, then you okay. Well, we used to have cards with chunk, and it's the same idea. That's a timestamp field. Remember, you'd usually punch in and punch out. This is when you started, this is when you ended. Those are timestamps. Point in time something happened. Normally, most database tables now, when you design a database table, you'll automatically add 2 fields to it. When was it created, and when was it modified? In other words, I'm talking about instances here, okay? So when, as a student, you were created in Algonquin's system. So that's basically when you did the registration, they put you into the database the first time, right? That would be your created value as a student. At this point, you have a student number, that's your ID. You have a name, whatever your name is. You have a created date, that's when your record was initially created in the system. And then there's a modified date, normally. When was it last updated? Changed. Something changed. For example, you got married, and you decide to change your last name to the name of your significant other. And this applies for boys and girls, because I've seen it done both ways. And the last name changes. That means somebody went to the system, modified your student record, changed the last name to be your new last name. Therefore, then the timestamp for the last modified date would change. Because then we can see, oh, this student was created 2 years ago, and we just modified their record 2 weeks ago, so we know when this happened. Timestamps are important. You need to know when things change. You need to know when things were created. For example, the created date is something they can use for stats on going, And they can derive what is the hump day when most records get created. Maybe we need to hire temporary staff for that 1 week to make sure everything handles nice and smooth. So then they can, handle that based on the created timestamps. Okay. There's a few additional fields depending on what you're doing when you design this table. One of them, depending on what kind of system you're working on, is, we had a created and a modified date timestamp I was talking about just 30 seconds ago. Sometimes you also have a who created and who last modified. In other words, who's the last person to touch that record? And then there's active or enabled. This doesn't usually apply to main records, as in for a student record. Actually, we actually have to active and active/enabled on students, right? You guys, somebody graduated last year, and they haven't signed up for any new courses. They're no longer an active student. So after a while, they just mark the record as inactive. It stays in the database because we need to keep track of it, but it doesn't need to show up in every search, unless I'm looking for people that have been deactivated. Going back to the first one about who created the field or last modified the field, I have a real-world example of this. Where I worked years and years ago, our shipping system was very trusting. As in, somebody could just place an order in shipping without going through accounting, and the guy in shipping would just take the order in shipping. The company was still learning to not trust its employees. And after a while, I was approached by the vice president of the company. He said, Dan, can you go dig through the database a little bit? I go, why? He said, something fishy's going on. And in the end, we discovered we had a tech support agent that was selling our software on the side, bypassing accounting. The only reason I was able to prove it was him is because the system actually kept track of every time something was created and modified, and it was stamping it with his user ID. But he didn't know this because this was all hidden data. He got clever, right? So he had them writing checks and sending them to a PO box. Until one of the customers actually sent the check to our front office. And we were wondering why there was a check that came in with the technician's name on it. Yeah, he was walked out the next day. But just say, problem is we could never actually charge him because we could never prove how many of these he actually did, because he was also modifying records to fix the customer's problems. So there was only so much a proof we had, so the system got much more robust, and you weren't allowed to do certain things anymore. It gave me 6 months worth of work, that kind of stuff. It kept me busy. But that's why it's important to keep track of who modified data. Now, for most of the database designs I'm going to ask you guys to do in this course, I'm not going to worry about created and modified. I'm pretty sure I still got another 45 minutes.
Yeah. Just checking it.
Yeah, I know. But that's what that is. All right. This is from a different diagramming software, but it doesn't really make a difference because essentially the concepts are the same anyways. When you look at the diagram, you'll usually have the field names, the data types, and some of the attributes that are on it. When you guys did it in Toad, the layout's a little different, but essentially all the same information. Okay, the next slide is the part where I get draconian about my grading. So this one's important. That's why I'm going to put the slideshow up. I might even give you a PDF that has these rules in it also, so that there's no excuse. When I grade your design assignments, I expect you to follow a certain naming convention. And naming conventions are very important. And one of the things you have to learn about naming conventions, you have to learn to be flexible. In other words, if you go work somewhere, they may have different naming conventions than the one I'm going to make you guys learn. I know for a fact that my naming conventions are a little different from Saeed, who teaches a different section of this course. Why? Because he teaches naming conventions that are in the textbook. I teach naming conventions that are used out in the wild. They're both valid. They're just slightly different. They're very similar, but they're just slightly different. So, naming conventions used to be loose and free. Whenever you started somewhere else, the naming conventions were completely different. Everybody had their own idea of how things should be named. And I think last week I discussed about A1, B1, or at least I did in the lab. And people named things whichever way they wanted, and it was just loose and free, no documentation, you didn't know what was going on. And originally, database servers had very limited space to work with. You know, you guys with the gigabyte/terabyte hard drives don't understand the concept of no room. Right? Your special collection of videos that take a ton of room on your drive, that's not really data, right? Doctor Who knows? Right, but that's, you know, but you don't understand, right? You're downloading videos that are in the 400 meg data range, 500 megs, gigabyte videos, you know, a terabyte of music on a secondary hard drive. Back in the day, we had real limitations. The first database server I worked on had a 100 megabyte hard drive. 100 megs. My phone blows through 100 megs in 15 seconds when I got a really good connection, right? But space was a limitation at one point in time. Naming convention used to be really odd. Table A, field A1, A2, A3. Why? Because they didn't have enough room on the server for nicely described field names. Each company had its standard. You name it this way, you name it that way. You use camel case, you use snake case, you use a combination of the two. And what would even be better is that each developer would have their own naming conventions and nobody was enforcing them. So there was rules and nobody enforced them. And that would cause all kinds of grief because you had guy A who named things a certain way and guy B who named things a certain way and lady C who named it somewhere in between, and suddenly nobody knew what the other person's stuff meant because they didn't follow the same rules. So it caused all kinds of grief, it added extra development time, tons of extra documentation, that kind of stuff. Now, what's happening is about 10 years ago, 15 years ago, what they call development frameworks showed up to the party. How many of you have heard the phrase Ruby on Rails? Okay, right? Ruby is a language. Rails was a framework. Rails says name your database objects a certain way and I'll make magic for you. You don't need to understand the underlying table structure because I can figure out based on what the database designer did. It's like magic. Ruby's a dead language. The framework survived. Go figure. Ruby didn't go very far. Because that was the big selling point of Ruby, was the framework, and everybody said, that's such a great idea, we'll do the same thing, and then there's no reason to keep using Ruby. What's happened though, is that a lot of these framework developers still, once again, I had my rules, he had his rules, another guy had his rules, and somebody said, this is such a stupid idea. People actually started talking for the first time ever. At least database designers, we like sitting in little caves by ourselves and, you know, not talk to anybody. But these guys started communicating and they said, you know what, if we start following the same rules, we can teach our database guys so they can work with more than one framework, as long as they follow some basic sets of rules. And what's happening now is a de facto standard that's slowly emerging out of the morass of mess that database design used to be. And essentially, the design that was created by Ruby on Rails was used as the basis, and then Cake PHP is another framework that's been around for a while. They took it and ran. Laravel, which is another PHP framework, adopted Cake's terminology. The Python one, I don't remember what it's called, Django, I think, adopted the same, almost exact same thing. So now everybody's following almost exact same rules. So it's not a real standard, it's what they call a de facto standard. It means that everybody agreed that they're going to follow the same rules. It's not written in an ISO paper where people spend $1 million writing a 55-page document to explain these 5 rules. I'm not kidding. There are literally ISO documents that are like 100 pages long to explain 5 rules. Okay, naming conventions are as follows. And when I give you guys an assignment, if you don't follow the naming conventions, I take off a point for every mistake, up to a set number of points. So let's say the assignment's out of 25, 5 of those points is naming conventions. I literally give you those 5 points. If you follow these 5 rules, you got 5 points for free. If you can't follow those naming conventions, I take them off mercilessly. And why do I do that? Is you guys got to learn to start following basic rules. When you leave the school and you get your first job, wherever you're going to work, they're going to have rules. There might not be my rules, but you got to learn to follow their rules. Thus, if I get you guys used to following a set of rules, you'll have that mindset in place. I mean, I lived it. If few years ago, I had to take a sabbatical, let's say, from where I'm working now, and go work somewhere else for a few years, and they had different naming conventions for everything. It took me 3 months to reprogram my brain from my old habits to my new habits. And thus, if you're at least willing to accept the fact that things are not always following a set rule, you're that much closer to the end of the game. All right, here they are. Everything is lowercase, no exceptions. And one of the reasons, actually, that a few years ago I switched this course to Postgres is that Postgres is anal retentive about its case sensitivity. It doesn't like mixed case object names. Field names, table names, doesn't like them mixed case, doesn't like them uppercase. It wants everything lowercase. And every database server out there except for Oracle is perfectly happy playing with lowercase. Oracle will accept lowercase, but it makes everything uppercase. Is your hand up? Question, or are you just flapping? Okay, no spaces in your object names. Use underscores. Okay, that means you have a person's first name. Okay, normally, I draw a little triangle here, there would be a space here. No space. Use an underscore. Thus, it still looks like 2 words, but it's connected using an underscore. Why? Because the language that database servers use to communicate, which is called SQL, uses space as its keyword delimiter. That means that if it hits a space in a field name, it assumes these are two different things, not one thing. So if you're going to want something that has first name, last name, mailing address, put an underscore between the words. Tables are plural. This is actually the one that's different between myself and Saif. He says tables are singular, I say tables are plural. That's because of this de facto standard that's slowly cropping up. Tables are plural whenever possible. Of course, there's always an exception to the rule, such as log. The phrase log assumes plurality, as in you're logging multiple things. So words that, if you're naming something and that's a word that assumes plurality, then of course, obviously, you're not going to stick an S on it, because that's wrong. But normally, if we're talking about a student, the table will be called students. And of course, that should be all lowercase. I tend to write in lowercase because my handwriting sucks. So uppercase is easier. So I got a table called, the table is called students, because this table contains many students, many instances of students. Primary keys. Remember earlier I said I was going to tell you what they're called? They're always called ID. Why? Because it's the identifier. Now, the data type, depending on the database server, will vary. Why? Because different database servers handle the primary keys differently. PK stands for primary key. Foreign keys. So for example, table A is related to table B. So we got a students table. Let's say we have a countries table. Of course, I made it uppercase, and I'm not rewriting it. This has an ID and a name field, right? The name of the country and the ID of the country. This is a reference table. It has 2 fields. The student lives in a certain country. Okay, country ID. Do you notice it's not countries ID? Oh, don't do this. That one died, but not that one. That's cool. I love technology in its classrooms. So foreign key names is singular parent name. So the parent value of this is coming from countries. What's the singular of countries? Country. underscore the name of the primary key. What's the name of the primary key? ID. Therefore, it's country underscore ID. Or users would be user underscore ID. Now, there's a few reasons why they chose this naming convention. At a glance, if you see anything that ends in underscore ID, look at the diagram, you immediately know that's a foreign key. It's getting its value from somewhere else. Next week I'm covering how this actually works. So this is the underscore ID. This is the for. This identifies that this field gets its value from another table. This side is the table name, the singular table name. So if you read country underscore ID, I go, oh, this is a foreign key. Country, what's the plural of country? Countries. It gets its values from countries. Therefore, you can derive the meaning of the values of the field, where it's getting its values from, based on its name. Because there's often, you'll end up in a situation where you get the dump of the database, an actual backup of the database, and no matching diagram. And if they follow a naming convention like this, you're set. Because you can figure it out based on the field names, what the values are that go from A to B, as opposed to having to guess. A1 gets its value from B3. I like that happen, right? Whereas if you have proper naming conventions, it follows it. These are naming conventions for this class. I'll be posting them on Blackboard probably sometime soon. Yes?
I have a question.
Yeah.
The example, it has capital for users for the table.
That's called PowerPoint mangling my text.
So we would use it as all lowercase.
Yes, you normally would use, but I used it, actually in this case, it worked also because it's a users table. It's a table about users. I put quote marks around it. But realistically, a table called users would be lowercase user with a foreign key of user underscore ID. Everything's supposed to be lowercase. It's just, I don't know if you've had a lot of experience with Microsoft text editing products like Word and stuff. It thinks it knows how to fix your text for you, whether you want it to or not. And if you take a slide from one to another, often it'll actually copy paste and correct your text for you. Then you're doing this at 2 o'clock in the morning and you don't realize that they use uppercase. I'm not saying I did that at 2 a.m., but it was about 2 a.m. when I was fixing my slides. Okay, now, that's the last slide. Yay. This week's lab is lab 3. It's basically put by the start of, in this lab, you should be showing me last week's lab if you haven't handed it in yet. In other words, if your lab is after this class, for those who have lab right after this class, you should be showing me your last week's lab if you haven't already submitted it to me. If you already submitted it to me, congratulations, you don't need to show it to me. But if you haven't submitted it, it's time to show it to me. But you should be working on lab 3, which is basically lab 2 with less hand-holding. Other than that, that's about it. Yeah, one more question. Okay? Jane, just come down, I can't hear you. Hold on.